Hi students, today in this video we'll be going through demonstrations and two demonstrations we are taking over here. Crystallization from a supersaturated solution and the second one is compressing solid, liquid and gases. The description if we see, exothermic crystallization from a supersaturated solution is demonstrated by pouring a solution of sodium acetate trihydrate onto crystals in a beaker, resulting in a column of solid that can be several inches in height. The purpose or goal of this experiment is reinforces the concepts of what a solution is composed of, supersaturation and crystallization. Illustrations or illustrated the concepts of exothermicity during crystallization. The explanation of this experiment is at temperatures below 58 degrees Celsius, solutions that are saturated with respect to anhydrous sodium acetate are supersaturated with respect to the trihydrate. The composition of the solution prepared corresponds to 88 grams NaC2H3O2 per 100 grams of water. The 100 grams of water includes both added water and water of hydration. When this solution is cooled to 20 degrees Celsius, it is unsaturated with respect to NaC2H3O2 but supersaturated with respect to NaC2H3O2 dot thrice H2O, that is 3 water of crystallization. Seeding the solution with the trihydrate thus causes formation of crystals of hydrated sodium acetate. Crystallization is exothermic and the resulting solid is warm to the touch. To demonstrate crystallization, place a few crystals of sodium acetate trihydrate into a 250 ml beaker and pour the solution onto the crystals. Do not do this too slowly since solids may start to form at the neck of the flask, eventually clogging it. Crystallization begins immediately, forming a mold of white solid sodium acetate. The beaker is used to prevent the solid from spreading too far. All the water is trapped within the solid, leaving no visual traces of liquid. The solid feels warm to the touch. The shape of the mold will depend on the manner in which the solid is poured. Pillars of different shapes and sizes can be produced. Hazards in this experiment are the solutions are hot enough to cause burns. If the crystallized sodium acetate touches the skin, wash with water because it may form the blister on your skin. Disposal. The material can be recycled. When disposal is wanted, the solid should be flushed down and drained with water. Let us take the example of salt crystal growing from the supersaturated solution. In this demonstration, sodium acetate crystal will be growing rapidly from the supersaturated solution of sodium acetate which is in liquid state. We are adding a small or tiny amount, say a pinch of sodium acetate salt into supersaturated solution. Is not it fascinating to see this crystals growing? A close-up view of crystal growing is in the right hand side picture. Now we can see that the solution which was in liquid state is now totally converted to solid mass. Now the total flask is completely solid. That is, when we are inverting the flask, it is not falling down. The second demonstration is compressing solid, liquid and gases. Here, compressibility is the property by virtue when the solids which are closely packed heated up gives liquid and liquids when heated up gives gases. Vice versa, when we compress a gas, it's converted to liquid and the liquid when compressed forms solid. The compressibility, solids are incompressible, gases are compressible. while liquids are very slightly compressible, that is, usually we say they are incompressible. If we talk about solid, in a solid phase, the particles are so close together, they are no longer having any free motion. In other words, they make a shape that won't change on its own and the particles set in place and vibrate. While in the liquid state, the liquid phase, the particles are closer together and are still free to move around each other. While in gaseous state, the gas phase, the particles are so apart and collisions occur rarely that if we apply the pressure, the gas can be compressed. If we see the intermolecular forces of attraction, the gases have very less intermolecular force of attraction between its molecules, while in liquids they have medium intermolecular force of attraction as compared to gases and solids, while solids have the highest intermolecular force of attraction between its molecules. Hence, gases can be compressed while liquid and solid practically are not in the position to be compressed. We'll be going through the demonstration where we'll be performing the experiment to see all these concepts of intermolecular force of attraction and the compressibility in the coming portion of this video.
Let us conduct demonstration to look more closely at some observable differences between solid, liquid and gas phases of matter. First, we are taking a piece of wood in a large syringe which is closed from the end of needle. Now we are going to push on the plunger of syringe to see how far we can push. We do not see any downward movement of plunger, so the solid as observed are not compressible. Now we are taking a greenish liquid in the same syringe where one of the end is closed from the needle side. Again we have applied pressure, that is the force on the plunger, so as to see the downward movement. We pushed more harder as we could, but the liquid was not compressible. So the volume that can be measured by the marks on the syringe are the same, proving that the pressure is not compressing the liquid to the extent which we wanted to compress. Finally, we are filling the same syringe with the air, the mixture of gases. When we applied the force on the plunger, and as you can see, the plunger is moving down in the syringe, so the gases are highly compressible. Yet another thing which we can observe was that first the movement was easy and later it became difficult to push as the volume decreases. This was figured out by Boyles. As the volume of air in syringe got less, the pressure by which the gas pushed out plunger